Okay, so in today's class, let me talk about design of autopilot. Now, first and foremost, whenever we talk about autopilot, autopilot means different in terms of different levels of closures of loops. The first and foremost thing for a UAV is it should be able to stabilize itself. What that means is if I set an airspeed, if I set certain course, before performing that maneuver, it should be able to stabilize itself. It should not fall down. It should not tilt. If it tilts, it should be able to come back. If there is a disturbance around it, it should be able to overcome the disturbance. So first inner loop is always stabilization. And please understand, if you are into RC flying, you can fly the aircraft using the joystick control, but the aircraft would have internal stabilization flight control. And the only thing that internal loop is going to do is it will stabilize the aircraft. If it's a quadcopter, it will make sure it is in controlled hover. If it's a fixed wing, it will make sure that it is in the level flight. And then you can trim the aircraft and then actually maneuver the aircraft, or for that matter, quadcopter. So if you look at the architecture, and we are going to study all of these, the only thing we will have issue is flying the aircraft, because we can't fly the aircraft. As a matter of fact, I want each one of you to have that trust certificate, because of it's very easy to weaponize a drone. So FAA and the law enforcement is becoming very strict in terms of drone usage, even for recreational use. So I can totally see that in next couple of years, if you start flying the drone, a cop can come to you and ask you for an FAA trust certification. You're supposed to have that certificate if you get asked by the law enforcement agency. If your drone is more than half a pound, that drone needs to be registered with the FAA and should. So as you go through that trust certification, you will see that the regulations are becoming stricter to make sure that drone flying is safe, and again, just to control that variations and malicious use. So just be consistent and be aware of what's happening. So first, we are looking at an unmanned vehicle or uncrewed vehicle. Then what we have is we have these different sensors. For an example, if you look at this Parrot Mambo drone, the Parrot Mambo drone has an ultrasonic rangefinder. Then it has a downward facing camera. It internally has an IMU. It also has the barometer, and all the data coming from Parrot Mambo is used for its internal flight control system. So you have these some sensors. Sensors are noisy. So what we do is we capture the sensor data and we do something called as estimation. What is the estimation? Estimation is the best possible guess. So we kind of fuse the data from different sensors and come up with the best possible estimate. That gets fed to the autopilot. So what we do is we combine the gyros and accelerometer data to make sure the aircraft is in level flight or is continuing with the desired pitch and roll. So once this loop is complete, then we go to a next level, which is the path following. So basically we give point A and point B. Following the path for the aircraft, it is very important. It is exactly similar to the trajectory planning that we studied in Robotics 1. In Robotics 1, we talked about how can a robot end effector go from point A to point B. In aircraft, we are doing exactly the same thing, but instead of the end effector, now we have a flying aircraft, which means we have many degrees of freedom that we can control. And after that, after the path following, what you have is you have something like a path manager. Because whenever an aircraft is following path, aircraft would never follow the path perfectly. There will always be some error. So you need some type of an error correction, which is the tracking error that is managed by the path manager. And then path manager is controlled by the path planner. So what would path planner do is you would say fly from tech to sim, and then path planner would create the waypoints, and then within the waypoints you would have a trajectory, and actually the path following will make sure that that teeny tiny piece of trajectory between two waypoints is followed, and then autopilot will make sure that the sensors on board is making sure that the aircraft stabilized and following airspeed, altitude, and heading, so that those individual waypoints, the aircraft can go from first waypoint to the second waypoint, second to third, third to fourth, and follow this sequentially. The next set is obstacle avoidance. All of a sudden, if you have an obstacle, then what? Next, then it's like flight in an unstructured environment. For an example, if the environment around the UAV is changing, which means the path needs to change dynamically. So how do you solve that? So there could be more and more sophistication as we go up. But first and foremost, we look at the autopilot, we look at the path following, and then gradually we'll look at the path follower. This whole workflow, we can talk about it for the fixed wing aircraft, but my hope is we will implement that entire workflow in this quadcopter, because quadcopters are easy to fly, safe to fly, and Mambo is an excellent platform for programming. So there are three main principles on which autopilots are designed. Now, first aspect is successive loop closure. And successive loop closure is not just for autopilot design. If you have a robot, if you have a 3D printer, if you have any machine tool that you want to control to perform series of specific tasks, successive loop closure is the simplest control that you can implement. So for an example, if you have a machine tool, and the machine tool has maybe, for an example, it needs to have some feeds, some speeds, some coolant flow, then material removal. So you have these different sub processes that need to happen to control the whole pipeline, start to finish. You can follow successive loop closure. So successive loop closure, I'm going to discuss in detail. It's a very general methodology. You can use it for controlling of not only the aerial robots, articulated robots, ground robots with an articulated arm, and so on and so forth. Second aspect is the total energy control. Total energy control principle is very simple. Energy can neither be created nor be destroyed. So if the energy is not changing, the system will continue to stay in the state the system is. So unless I drink caffeine or unless I do something else, my energy level is going to remain the same. However, so what I'm going to do is, if I want my system to be simply stable, I would just check the rate of change of energy. If that rate of change of energy is 0, which means the total energy is remaining constant, system is simply stable. If that energy is decreasing, the total energy is decreasing as time goes on, system is asymptotically stable. If the system energy is increasing, the system is unstable. If you take courses in linear system theory, then total energy control technique is something similar to the Lyapunov based technique. So if you use Lyapunov based technique, that is nothing but the total energy control. LQR control is called optimal control, linear quadratic regulator, which is for LQR. Typically, total energy control and LQR control, those are discussed at the graduate level. So I would briefly go through it, but I'm not going to discuss total energy control and LQR control in detail. But I would encourage you, if you have had some background in linear control systems, or if you have taken course from Professor Zhang related to control and optimization, then I would encourage you to take a look at the total energy control and LQR control. LQR control is an optimization technique. At the core, optimization is taking the derivative and equating this to zero. Constrained optimization means you have some equations that are restricting the evolution of state. And what we have is, we have this dynamical equation of motion that has to be valid all the time. So that becomes the constraint when you are doing LQR control. So there is a geometric interpretation of LQR control, and there is just a mathematical interpretation of linear quadratic regulator. So I would encourage you to review that if you are really interested in becoming a controls person, or take some courses in linear control theory, or take classes control and optimization. Okay, successive loop closure. This is a very simple technique. In last few classes, what did we talk about? We talked about, we have these nonlinear equations. And what we did in this nonlinear equation, somehow we linearized part of that nonlinear equation. And part of that equation could not be linearized. We treated that as a disturbance. And we designed, or we had a block diagram wherein the external control input is able to overcome the disturbance and also control the system dynamics. Now, if you understand, in the last class, in the linear control model, at the end of the day, we had a cascaded transfer function. You remember that in the linear control model, longitudinal dynamics or a lateral dynamics, at the end of the day, after you did all that, we had transfer functions that were dependent on each other. Everyone understood this? Now, what needs to happen is, we have to find out what is the most critical function, or what is the most critical loop. So for an aircraft, stabilization must be the internal loop. So what I'm going to do is, I'm going to design a control algorithm so that internal loop becomes one. So this, which means whatever is the input becomes the output. So internal loop becomes one. The only thing that you have to be careful about is the bandwidth, because what needs to happen is the innermost loop must be the fastest loop. Then gradually, as you go outer, then your loop will slow down. But you need to make sure that the innermost loop is running at maybe 1000 hertz. Then what you have is, so what you do is somehow add the controller algorithm so that the gains, so that the inner loop becomes one. Now I need to specify. So here is the physical understanding. Imagine at the end of the day, if you have an aircraft flight control. What is an aircraft flight control? At the end, it is going to deflect those control surfaces. So deflection of those control surfaces will be done with some actuators. Now the actuators need to be moved. So pilot is not going to move the actuators by hand, but it's going to actuate a lever. This motion of this lever needs to be amplified by a gain that results into the motion of that huge amplifier. Think about power steering. You move the steering a little bit in one direction, but your wheels turn a lot. So exactly the same thing, which means when we try to close the inner loop, we tune the gains and the system parameters in such a way that the inner loop becomes one. That is the principle. So once innermost loop becomes one, How do we make it happen? Once again, whenever pilot is flying an aircraft, you have this control system, you have this something like power steering mechanism that is actually amplifying the pilot stick input to move those heavy control surfaces. So we have to adjust the gain of the system so that the input from the pilot is able to overcome the external disturbance and the system dynamics. But at the end of the day, we will adjust the gain. We will adjust the gain such a way that the inner loop becomes one. So that is the inner loop closing. Afterwards, once the inner loop is closed, what we will go to the next loop, and then we will adjust the control and we will adjust the gains such a way that this outer loop is one, and we will continue this process to all the way to the end. So once this whole thing is balanced, you pretty much have all the loops closed, and then you have a flight stabilization, or you can use the same technique for path and other controls. So the idea is, once you have a cascaded transfer function that we generated from the lateral and linear dynamics, what we do is we successively make all those internal loops is equal to one. And this techniques in practice works very well. So next thing which I want to talk about is this inner loop. How do we actually close this? And what we do is, it starts with the dynamical, the linear model that we developed in last chapter. So this is the lateral directional model. I don't know if you remember this, but after spending more than 3 or 4 lessons on chapter 5, finally we got this lateral dynamics transfer function, wherein you have those external disturbances and you have these controller gains. So what I'm going to do is, I'm going to take this roll control and I'm going to reduce that block diagram to something like this. I'm going to reduce. Once you reduce, and we did this block diagram reduction in robotics 1, wherein we combine these blocks, and after combining this block, we got this big transfer function. And remember, we linearize. So which means whatever we are going to get is all linear. And whenever you have a linear system, the beauty is at the end, it will be in the form of spring mass damper system. So now I want you to observe this. Please note, this after reduction, you have this equation S square 2 zeta dr omega 1 S and omega n dr square. Believe it or not, this is the transfer function of a spring mass damper system. Mx double dot plus Cx dot plus Kx is equal to f of t. That is the transfer function. The only problem is, very important, that this spring mass damper function transfer function is multiplied with another pole, which is S plus PSP, and then on top you have another spring mass damper function. But as soon as the transfer function is in the form of spring, mass, and damper, you can control the behavior of that system. And I know all of you know this, but for my own satisfaction, I'm going to write this down, because here is what's going to happen. Once you linearize, this is the beauty of this approach. Once you linearize, and then you treat all the non-linearity as a disturbance, and once you combine all these transfer functions into one big transfer function, that transfer function will look very similar to a spring mass damper transfer function. And what I want to do is, I just want to make sure that it's for my own satisfaction. this is mass, this is K, this is C. So the equation is mx double dot plus cx dot plus kx is equal to say u of t. Now where x of t is the output, u of t is the input, and understand, if I increase the damping, the system response kind of dampens. If I increase the stiffness, basically what happens is the natural frequency increases, so you get oscillations like this. What that means, if you have this axis, real axis, and if you have an imaginary axis, if I increase damping, my poles go towards left-hand side. And if I increase spring stiffness, basically my poles travel in the vertical direction. So what I have is, I have this equation. I'm going to take the Laplace transform. So I have x double dot, which becomes m s square x of s plus c s x of s k x of s is equal to u of s. Now u of s is the input, x of s is the output. So I say x of s is equal to u of s is equal to 1 divided by m s square plus cs plus k. This equation can also be written as s square plus c by m is defined at 2 zeta omega n s, k by m is omega n square. So this spring mass damper system, its representation x of s divided by u of s is something like this. And why is this important? Because the transfer function that you see here, it has the term like zeta omega n square. So what that means is you can tune the values of c, or you can tune the values of zeta and make system behave the way you want. Everyone understood this? That is why we perform the linear analysis. So as you can see, the roll control, that whole equation can be modified. And then if you look at the equation for the yaw damper, and what is yaw damper? So there is a concept which is called as the Dutch roll. So what I want to tell you is, for example, if because of roll and yaw coupling, what happens is the aircraft is going to go like this. And why is this called a Dutch roll? Is because I think this is how the penguins walk. So if you look at the aircraft, it's going to go like something like this. So to compensate this not required motion, you have that rudder. That rudder continuously compensates this motion, and so we add a yaw damper. And I want you to understand the equations that you see will be in the form of a spring mass damper system. So if you go to the next slide, if I want to implement an autopilot in roll, if you look at the closed loop transfer function for the roll autopilot, which is canonical, which means similar in mathematical form to the second order transfer function. So you can tune the gains of this transfer function based on the spring properties and the damping properties. Now here comes the next important question. So we talk about tuning the spring. We talk about adjusting the damper. How is it done practically? The way it is done is basically, if you have a damper, so if you physically want to change its damping properties, you can replace the damping fluid. So if you have a less viscous fluid, then the resistance offered by that fluid will be less. You can actually replace this damping fluid to more viscous fluid. The other way this can be done is many a times you have small hole here or small orifice here that kind of restricts the amount of resistance the fluid faces when it goes from one chamber to other chamber. You can actually change the diameter of the orifice. Sometimes what you can do is you can have external valves that open and close. For an example, you can have a valve here and you have a valve here. If you want to reduce the resistance of the damper, you'll open this valve and this valve so that this piston can slide easily. If you want to tune the damper, if you want to change the resistance of the fluid, then just close one valve, open one valve, and so you can tune this damper either intermittently or you can make gross changes. So that is how the damping coefficient is changed. In terms of springs, you can adjust the preload on the spring, or you can change the type of spring, or you can change the geometry of the spring, and then you can adjust the spring coefficient. So it is in practice, typically, if you want, it's possible to change the damping properties, and it is possible to change the spring properties. Many a times, the actuator is sort of combined together. So for example, have you seen the shocks of your automobile? What you have is you have a damper and you have a coil spring. So you could have an integrated actuator wherein you have the spring and you have the damper and you have the actuators that change the preload on the spring, and you have the valves that control the fluid flow, so you can tune the damping coefficient. Everyone understood this? So that is how it is done in the practical aircraft systems. So the point being, this what I'm showing, which came from the last class, at the end of the day, it's going to become a second order transfer function, a form of second order transfer function. And you can tune the second order transfer function gains by changing the values of Kp or changing the values of Kd. And at the end, you would have this delta A, which is the actuator command, which is some coefficient multiplied by theta C, some coefficient multiplied by the P. So basically, and again, I just want to tell you that other way to look at it is you are using some type of a PID control. So a term which is dependent on the position and a term which is dependent on the velocity. Once you look at the practical implementation of control, whenever we say PID control, the PID doesn't have to work on the same state. What it means, if you have a multivariable system, if you want to design the control, you can take position of one mass and you can take velocity of the second mass and still design the control, and it will still work. So there are different flavors of it, but at the end of the day, whether you work in state space, whether you work in transfer function, and in the cases of linear systems, it's all one and the same. So this is some form of PID control, because check this out. This is PC, which is the control, P, which is actual. This is the error multiplied by Kp multiplied by the rate, which is P, roll rate, minus Kd. So this is a form of PID control. Everyone understood this? Any questions? This is very practical, because I tell you, when I went to working on Bell 609, as I said, tilt rotor, they said we use velocity feedback. I thought, oh wow, this is something like a model predictive control. At the end, when I looked at the loops, they were simple PD loops. Usually integrator, I have not seen integrator being used, but typically use PD loops. And if you want to make it more sophisticated, and it's not possible for this example, but you can actually use some type of MPC control on a plant and then implement model predictive control. but we will talk about it when we get there. But at the end, we have a transfer function that resembles to spring mass damper transfer function, and we use sort of a PID control to control the behavior. Again, the point which I was trying to say, that integrator, if you read the book, this is integrator, but basically integrator is not used in practical application because of the wind up, and if the issues, if you have gain scheduling, the integrator is not needed, and integrator could add delays and could give rise to instability. Now, so what's going to happen is all the functions, all the transfer functions that you have in the innermost loop, here is what we are going to do. We are going to adjust the KD, this guy, and we are going to adjust the KP, that guy, so that this internal loop becomes one. Everyone understood this? That's exactly what we are going to do. And that is internal loop closure. And then we are going to go outside and close the outside loop. So for the outer loop, which is the course hold loop, what we are going to do is, if you combine the transfer function for the course hold loop, so if you want to maintain the same course, again, I want you to pay attention. The transfer functions that you see are some form of spring mass damper system. But if you see the transfer function in the numerator, it does not have any mass. But if you see the transfer function in the denominator, it has a mass component, it has a spring component, and it has a damping component. Only thing is, those spring, mass, and damper, they are described by different physical quantities. Check this out. You have Vg, G. So those components are describing the damping, and then you have Ki, G divided by Vg. That is describing the spring component. So once that is all done, again we are going to tune the Kpx and Kix so that this inner loop becomes one. And again, if you are hardcore control theory or linear control systems guy, then you can actually see that you can make this understand the issues of adding zeros in the transfer function, which is like adding term that makes the numerator 0, or then you can study the pole and you can do the root locus, all that type of analysis, and then try to tune the performance. And please understand this performance curve. On the left hand side, what you have is you have what is on the left hand side? Body plot. Remember body plot? Okay. So on the left hand side, we have body plot. What is this body plot telling me? Body plot is telling me, as I sweep the frequency from 0 to very high frequency, how is the system going to behave? And as I can see that it has the 0 magnitude initially, and then the magnitude kind of goes down. So as the damping coefficient increases, system response dampens. And on the right hand side, what you have is you have the time domain response. Remember, frequency domain response, body plot, time domain response. So you can use these tools to control or tune the gains. Okay, going back to the course hold loop, and you realize that again you have a transfer function that looks similar to the transfer function of the second order system. And then what you do is you tune the Kpx and you tune the KIX so that that inner loop becomes 1. The next part is a little bit digging deep into the yaw damper. If you look at the transfer function of the yaw damper, you have again a second order system in the numerator, and you have a second order system in the denominator. And clearly it's a third order function, so you have another pole, but you can actually adjust those locations of the poles and control the system behavior. And again, you have something called as the washout filter, which is given in the denominator. So you have this filter. This is the summary of lateral autopilot, wherein you have an inner loop, you have an outer loop, and you have a yaw damper, and you are going to adjust these different parameters so that all those loops get successively closed. Now, for the lateral autopilot, how it is done in flight. Please understand, depending upon the flight condition and disturbance, those controller gains need to be tuned. Either the pilot tunes them, or sometimes you have an autopilot system or a flight control system that adjusts the gain. So those internal gains, you can be for inner loop, you have KD that needs to be increased, you have KP, then you have KPX, KIX, and tau R and KR. Now this is something similar to how you tune the PID gains. There is no right or wrong way, but there are some guidelines that you can follow to come up with the best possible gain values. And some of these are the guidelines that are given to you, like you increase the KD all the way to the instability and then get it back all the way by 20%. So what does that mean? So change KD so that you are here, and then all of a sudden go back by 20%. So you get this much amount of stability margin. That's what it means. And then KP is like you look at the step response, because KP dictates how fast or how slow the system responds. The problem with KD is if you increase KD, which means if you increase damping, the system becomes sluggish. You don't want that to happen. You want system to dampen the oscillations, but you want system to respond to the inputs quickly. So you have to balance these two. Same thing for outer loop, then same thing for side slip hold. So these are the design guidelines that can be used. Now in longitudinal flight regimes, we are going to see the same thing. We are going to have a long transfer function. We are going to break that transfer function into small pieces and adjust the gains so that the internal piece becomes 1. Then the next piece next to it becomes 1, and gradually everything becomes 1. So if you have altitude hold, which means you want to make sure that aircraft is flying at constant height, you have an inner loop. Please understand again, second order transfer function. Then you have KP theta, which is the proportional gain. You have KD theta, which is the gain on the velocity. So adjust KP theta, adjust KD theta so that this block, the whole block becomes 1. That is the trick. And for every aircraft, these values are different, because for every aircraft, even though the transfer function may look the same, individual values will be different. For the same aircraft, when the aircraft is flying in a different regime or a different airspeed, the transfer function form will look the same, but the values will be different. That is where we will talk about it. We will do gain scheduling, which means we will adjust the gains depending upon the regime that the aircraft is flying in. And again, for pitch altitude, sometimes the problem is you cannot continue to give control input infinitely. There is a physical limit to the control input. So there is something called as the saturation that makes sure that even if you increase it beyond certain limit, that the control input gets saturated, because that is the physical limitation on the hardware. The pilot, so if the lever can go from here to here, you can't prescribe the control input that asks pilot to push lever all the way over here. So there are physical limits. So you will see, even in quadcopter control system, you will see saturation function because of the physical limits on the hardware. Again, you have Kp theta, Kd theta, and finally you have this DC gain. And at the end, what you do is you take this internal loop, adjust this Kd theta, Kp theta, so that internal loop is 1. Now you can, and these are the same equations that we derived as part of last chapter. Again, same thing. We take this transfer function and then reduce the block diagram so that we have a transfer function, and then we actually independently control the system parameters or tune the parameters so that the transfer function is 1. And again, here you have Kp, Kih and Kph. Again, they are derived from the transfer function, which is the form of the second order transfer function. For airspeed, using throttle, so you want to maintain the constant airspeed. If you look at the linear model for the airspeed control, this is the linear model that we derived for airspeed control. You reduce the block diagram. After reduction of this block diagram, you are gonna get something like this. VA is equal to VAC, which is the commanded, and then which is the DV, which is the date variation. So, or this DV comes from the disturbance. So this guy is representing the transfer function on the disturbance. And then for that, you will adjust the KPV and KIV, the KPV and KIV, so that this transfer function becomes 1. Now, next part is using the finding out the gains. And the way you will do the gains is you can use this throttle delta T as a PID or PI controller. So for example, this is the proportional control and this is the integral control that is used to make sure that the system doesn't overshoot. So you can use the KI control for controlling. And this is the summary of longitudinal autopilot. Just like the lateral autopilot, the idea is you have derived all these linear models, combine those block diagrams, and finally get a transfer function with some numerator, with some denominator. And this innermost transfer function, you adjust the gains, 2 types of gains, Kp and Kd, Kp and Kd, adjust these gains so that this whole thing becomes 1. You do the same thing for lateral, you do the same thing for longitudinal. You have an inner loop, you have an altitude hold loop, you have an airspeed hold loop, and you have a throttle hold loop. So once you control these loops, basically you have a theoretical autopilot that you are ready to implement on hardware. And again, just like lateral autopilot, these coefficients change depending upon the airframe, depending upon the weight, depending upon the flight regime. And these are the tuning guidelines for different loops. So again, there is no good or bad method, just these methods have worked in the past. So these are the best practices. And then this is the most important part. And in our project, we are going to implement this in a successive loop closure. But I just want to talk about these implementations. I will when we do I will show you the project. I will talk about the implementations because please understand, we are going to implement these control algorithms or autopilot algorithms on a discrete hardware. The sensor data that is coming to us is in discrete domain. It's digitized. So we have to, even though we have the equations for continuous transfer function, you need to convert those into the discrete. So next part is the total energy control. And again, this is based on the Lyapunov technique. Question.
When you say the internal loop should be, the gain should be one, so the idea, intuitive idea is to get a more reactive thing. Given input, you should get the actual equation.
Yeah, so basically whatever is the input should become the output.
The problem is when you say that y of s upon x of s is equal to 1, when you equate that with the transfer function, I'm assuming he adds some random value to kp kd. What about the s value over there? When we are dealing with three variables, like kp kd and s itself.
No, S is an independent variable in the Laplace transform. So S is an, in time domain, the independent variable is t. In the Laplace domain, the independent variable is S. So this transfer function, the tunable parameters are theta and omega n. Theta is dependent on kd. Omega n is dependent on kp. So once you tune kd, theta gets changed. Once you tune kp, omega n gets changed. And once essentially you place the pole of the transfer function, or you tune the eigenvalues of the state space model to wherever you want.
So is it like we take the root locus, we get the
We can take the root locus, correct?
we get the solution of the characteristic equation, and then we get kp kd value, and then we continue to get proper kp kd.
Correct. So it's just like PID tuning that we studied in robotics.
Equating it to one doesn't give much of help while tuning.
So, but you have to start somewhere. So the idea is, that's why you have these guidelines. Like you start with, first you go all the way to region of instability, move it back. That is, then you fix, that is the value of KD, and then kind of adjust the KP so that it gets to the desired response. Okay, so total energy control is based on the Lyapunov technique. I'm not going to talk about the math behind this technique, because it is shown that in some cases, it is shown that successive loop closure yields better result than total energy control. But the idea of the total energy control is you have kinetic energy and you have potential energy. And you find out the rate of change of energy, total energy. If you equate that to 0, that means the total energy is remaining constant. That will ensure the system is simply stable. If that becomes negative, system is asymptotically stable. If that becomes rate of change of energy becomes positive, that makes system unstable. So what you do is, for the dynamical system, such as an aircraft, you find out the kinetic energy, you find the potential energy, and you find out the energy rate. And this, so you do energy rate calculations. And then the problem is, even though people have shown that this technique works in simulation, this is nothing but one form of Lyapunov technique, which is the energy-based technique. But unfortunately, this system, this equation, or this technique does not work the way we want it. And primarily because many a times the control functions that you are going to get from applying this could be nonlinear. But I would encourage you to go through this the equations. So the idea is you design the PID control based on the total energy. And you design the PID control based on the energy distribution. So again, this is called as the Lyapunov function, that is indicative of kinetic energy and potential energy. Remember something that we did in robotics 1, Hamiltonian. Hamiltonian was the difference of kinetic energy minus potential energy, E minus B. and we use T minus V to derive the differential equations. Remember, we use MATLAB, that MATLAB created the differential equations, then we numerically integrated. Lyapunov function is again kinetic energy, potential energy, but you add them together for the total energy. And then you design the total controller so that you control the total energy, or you control the energy rate, or you control the energy distribution. So that is the total energy control. And the problem is at the end, most likely you are going to get a nonlinear controller, and the nonlinear controller, it looks good on paper. It may show better controller results in simulations, but when you implement, there are some practical issues. You need a floating point. You have to perform floating point arithmetic. You need faster processor. You need to make sure that you don't have any division by zeros type of errors. And you may have to make sure that the system converges to the actual value. Because if you have a function like sine theta or cosine theta, please understand, computer does not know sine theta, does not know cosine theta. It evaluates sine and cosine theta using some type of successive approximation. That approximation should be accurate enough in the teeny tiny time that you have to complete that calculation, so that the value from that approximation matches the actual value. That is where the difficulty lies. Okay. Now I will talk a little bit more about this total energy control and the LQR control. But I want to ask you, we have two options at this point. Either I can show you the simulation for the current project, and you are welcome to make sure and just check if your answers are matching, or if you have any doubt related to your simulation, or I can show you the little bit Mambo, the demo for the Mambo. So what would you prefer? Let me see.
Is the video of the code that we walked through last class uploaded?
Yeah. Oh, by the way, somebody posted the Paulo Air, PABLOAir.com. So, okay. So what I'm gonna do is, I'm gonna just, yeah, the video for the last class is already online, but just for my, again, for my own satisfaction, what I want to do is, I want to go to chapter 4, and I want to show you the Simulink model. And I just want to show this to you so that if you have your Simulink model, you can quickly check that. So if you go to MATLAB 2022B, this is going to be your next assignment, wherein you have these mini drone virtual labs. They actually talk about the simulation and flight control, model-based design. So this is going to be your next assignment. But I just, yeah. So please download and install MATLAB 22B. Okay, I don't know if I set the environmental variables correctly. Yeah, I haven't set environmental variables correctly, because it won't be able to find draw aircraft function. Okay. So MAV Dynamics. Does anyone want to take a look at any code here? Yeah. Okay, wind simulation code. Yeah, that's sufficient. And if you want to take a shortcut, what you can do is you can go to MATLAB aerospace block set, wind, and there is actually a wind model that you can grab. It will do the exact same thing. Okay, so this is the wind simulation. Yeah. Yeah, of course. Can't do this simultaneously. Okay. Any? Ah. Okay. And what I want to show you is so if you go to Parrot Mambo, so mission support for Parrot Mambo. We can use these blocks. Any other question, other blocks? Yeah. So you have to specify these initial values. VA airspeed is 25, LU 200, LV 200, LW 50, and then you can add these gust factors. If you don't want to deal with it, what you can do is you can go to library browser. You can go to aerospace block set. Then you can go to wind environment. You can go to wind model, and then you can actually get a discrete gust model and then grab it and drop it over here. So what this will do is once you send the airspeed to this V25, it will actually give you the wind model. So it will give you gust in U axis, gust in V axis, gust in W axis. Yeah, wind simulation. So that wind model is actually implementing all this. Yeah. Yeah. And please understand, this assignment is a little frustrating. So if you get stuck, just stop by my office and I will help you, okay? Just send me an email. I would be more than happy to help you with this assignment. So please bear with me. This may be a little frustrating and then, but we will get through. Yeah.
So just out of curiosity, for this specific simulation, program, which block is that supposed to be plugged into?
So if you don't want to deal with this wind simulation, you say, I don't want to use this. What you can do is you can go to this aerospace block set. Aerospace block set. You will go to environment. You will go to wind and grab this discrete wind model. Grab it over here and place it over here. It's going to need an input. It's going to need an input airspeed. V stands for the airspeed. So you need to supply a constant airspeed, and then it will give you the corresponding wind models, corresponding wind values. So as you can see here, wind gust. Can you see here? What you can do is you can grab this and place this block instead of this gust. And then add a constant of 25 or 35, whatever airspeed. You will need the mux because finally it's going to combine all that and feed it over here. Yep. Yeah, you will need this C block. So basically, if you click on this C block, let me see, wind north. Yeah, because this is wind N, wind E, and wind down. This structure requires this northeast downwind. And this wind gust is going to give you U, V, and W. So the other way to do that is there is another wind model that gives you turbulence. Yeah. So you can use an appropriate wind model and then feed that data to this. So, okay, any other questions? Once again, if you need help getting this done, do not hesitate to reach out to Jacob or Tatvik. Or of course, I'm at your service. So my office hours are after every day at 7:15 after my class. Shoot me an email, stop by, and I would be happy to go through your model or show you my model so that you will have a good understanding. But please understand, this is important. And when is this due? Oh, tomorrow. Okay, I'll give an extension. That's okay. Yeah. Yeah. Yeah, tomorrow, I don't think you will be able to get it done by tomorrow. Yes, sir. Uh, I'll do it at first. Yes, happy? Okay, all right. So I'm gonna stop here.